Okay, hello everybody. I'm going to talk today about face recognition. Understanding face recognition is a topic that occupies many scientists busy. Those scientists typically come from two main disciplines, either the cognitive psychologists or the cognitive neuroscientists who are interested in understanding how the brain can recognize faces. And on the other hand, we have the computer scientists and the engineers who are trying to develop algorithms that can recognize faces. The reason face recognition is a topic that many people are interested in is, so from the point of view of the psychologist, is that face recognition is actually critical for social interactions. So think about yourself coming into this meeting today and being unable to recognize any people in this meeting. That would really limit your social interaction with people you are supposed to know. So this would be one reason why this is actually something that we do in our daily life and is very important. From the point of view of the computer scientist or the engineer, there are today main two applications for face recognition. One is coming from the social network, Facebook and all those different social networks that many of you, not me, but many of you uploaded so many pictures of yourself to Facebook. And they have millions of pictures of many different people, and they want to be able to develop algorithms that can recognize the people in those very different pictures. And the other one are the security forces, so police and FBI and all those different agencies that want to use face technology to recognize suspects. And they're even willing to pay a lot of money for that. So this is a new software that they recently bought for $4 million. So I think if somebody is willing to pay so much money for the face recognition software, there will be many people who will try to develop such a software that will do the job very well. So the reason so many of us are working on this field of face recognition is because face recognition is actually a very computationally demanding task. So it's very hard to both understand how the brain is doing it and to understand how to build an algorithm that is doing it. The reason it's complicated is because we are asking the system to perform two contradictory or opposing tasks. On one hand, we ask the system to be able to discriminate among many, many different faces. So we talk about could be thousands of faces or millions of faces that all have pretty much similar structure, but at the end they are different from one another, and we need the system to be able to discriminate between them. So this by itself is a doable problem, but at the same time, we also ask the system to be able to take many different pictures of the same individual and be able to say that those all belong to the same individual. So on one hand, we have we ask the system to discriminate among many faces. On the other hand, the need to generalize across different images that are actually very different from one another, maybe more different than two images of two different people. Okay, so this is the main challenge, and the main challenge is both the psychologist is trying to understand how the brain is doing it, and the computer scientists are trying to develop the algorithms. So in that sense, the two disciplines are actually using two different approaches. What the people who are coming from machine vision are trying to do is that they are first trying to develop the algorithm, so that's their job, to develop the algorithm. They need then later to determine what will be the input, so they come with a set of images that they train their algorithm with, and during this training the algorithm is learning the type of images that it's supposed to then be able to discriminate. This is then done by examining the performance of this algorithm on a new data set of images, and the goal at the end of all the machine vision algorithms is to outperform the human brain, to do it better than the human brain, because it's so far considered that the human brain is doing it the best, but I think the algorithms in the past few years have gone a long way, and they're actually doing a pretty amazing job. On the other side, we have the cognitive psychologists, the cognitive neuroscience, who are trying to understand how the brain is doing it. We have no idea what is the algorithm. We don't know how the brain is actually recognizing faces. This is what we're trying to study. We also don't know what is the input to the system. So we know that when the subject is coming to the lab, he has been exposed to many different faces throughout his life, and this exposure, and this is something that I'm going to talk about in the second half of my talk, this exposure to faces is very important for us to then develop our face recognition ability. But when the subject is coming to the lab, we don't know what was the kind of experience that he got before. We test the subject in the lab, we present them with different faces, and we see how well he can do with the different tasks that we give them. And the ultimate goal is to deduce the algorithm, to try to understand how the brain is doing it, how does the mind work at the end. So these are basically seem to be very different approaches, but what I want to try to show you today is that by combining these approaches, by having both type of approaches in our mind when we try to answer these questions, so by trying to combine these two approaches, I think we can, both fields can benefit from that, and I think we can make progress in understanding face recognition. So in the first half of my talk, I'm going to talk about an experiment in which we try to combine the computer-based and the human psychophysics approaches to understand what we use, what information we use to recognize faces. And in the second half of my talk, I'll talk about the type of input we may want to provide this system, we want to provide to the brain in order different images, and for each image you construct what is called a feature vector. So each face is going to become now a feature vector, a list of numbers that depict the information that we extract from the face. The information can be very different for different algorithms, but at the end, for all of them, what you have is a list of numbers that describes a given face. What we usually do in psychology, we bring subjects to the lab. Usually they're not so happy, but we try to make them happy by running experiments in which we present them with different type of faces. And what we have at the end is we collect data about perceptual similarity judgments that they make about the faces. They need to decide about two faces whether they're the same or different. And we see how the different manipulations that we make to the faces are going to influence their discrimination ability. So in the experiment I'm going to show you now, we try to actually combine these two approaches. We actually wanted to, we care about how the brain recognizes faces, but we want to see whether we can find the feature vector that the brain is using to do that. So how we can define a feature vector for specific faces. This is an example. Basically, faces are very complex stimuli. We can divide them or describe them as different, as multiple feature stimuli. So for example, in this case, we have two faces, and we can describe them on a two-dimensional space. On the x-axis, we may have eyebrow thickness. On the y-axis, we may have face roundness. So in that case, George is going to be here. He has round face, and he has thin eyebrows. Kramer is going to be here, okay? So each face basically can be described as a point in a multi-dimensional space. Here I have only 2 dimensions, but we can have more dimensions, and I'll show you in a second how many dimensions. But the important thing is that if we bring now another face, and we again put him in the same face space, we want that 2 faces that seem more similar to one another will also be close together in our face space. Okay, so the face space distance between 2 faces that are perceptually similar should be smaller than 2 faces that are perceptually more different. Okay? However, the main problem is that we don't know what are the features. So thinking about faces as point in a multidimensional space is something that we actually familiar with in the cognitive psychology literature. But so far, nobody has found what are those dimensions. And once we find those dimensions, we will be able to know what are the type of features that the brain is using to discriminate between faces. So this is the study that Naftali Aburdaham in my lab, is a PhD student in my lab, was designed in order to be able to find what are the critical features we use to recognize faces. We came up with 20 facial features. This is actually the features that are used by the FBI when they're asked witnesses to describe the faces of suspects. So we came up with 20 facial features, and now the question is whether those features are important. So how do we know? We take 100 faces, and I show you just 4 of them here, and we ask subject to rate each face for a given feature, okay? So, for example, here it would be lip thickness. This guy has relatively thick lips, so you would get +4. This one has relatively thin lips, so you would get -3.5, for example. Here about hair color, okay? So we do it for each of our 20 features, and we end up with a feature vector that is based on perceptual judgments of different subjects for each of our 100 faces, okay? So these feature vectors actually represent the relative importance of the different features. So if this guy has relatively thick lips, then he's going to get a relatively high score on his lip thicks, and he has relatively bright hair color, he's going to get a relatively extreme score on his hair color. So once we do that, we can describe each face as a point in this multidimensional space, and we can compute the distance, the face-face distance, the mathematical distance between those 2 faces, and then try to see whether this mathematical distance is related, that is based on those multiple features, is related to our perceptual similarity of the faces. So for example, these are two faces that had relatively short face-space distance, and when we show them to subjects, they would say that they are relatively similar. Those have relatively large distance in the face space, and when we show them to subjects, they would say that they look relatively different. Okay, so these are different faces with large face space distance. These are relatively similar faces with small face space distance. So basically what this shows is that by using those 20 different features, we were able to reverse engineer the face space. So we were able to find out what are the features that we use to recognize faces. However, we may not use all 20 features. What we want to do is which features are the critical ones. Which of those 20 features are we use for the face recognition, which we may not use. In order to do that, what we did next is we actually changed some features, and by changing the feature, we're actually moving our face in the face space. So if we change the eyes, round eyes to thin eyes, or if we change the hair color, this would move the face to a different location in the face space. This is how it's done. So this guy has thick lips. We replace his mouth with guy with thin lips. He has thin eyebrows. We replace his eyebrows with thick eyebrows, and we get this new face. And by doing that, we move the face to a different location, and then we ask subject how similar are the two faces after we make those changes. So we then look at the correlation between the difference of the original face and the changed face in the face space, and the perceptual judgments that we get from people of how those two people, whether they look the same or not, and this is the correlation. So the correlation between the difference that we found in face space and the similarity judgments is actually highly correlated. Now this is based on all 20 features. Now we want to know which of the 20 features are the critical features. One thing that we realized is that when you ask subjects to judge the similarity of different features, there are some features that are easy to discriminate and some that are harder. So for example, the lip thickness is easy to judge. It's easier to see that the left guy has thicker lips than the right guy. But if I ask you to judge the eye distance of those two different people, it will be harder to tell which of those people has closer eyes or farther away eyes. So we actually were able to list those 20 different features based on how easy it is or hard it is to determine whether they are different or similar across different faces. And what we did is then we took only those that are higher up here, only those that are easy to discriminate, the hair color, the eye color, the lip thickness. We compute the face-space distance based on these features. And what we found is that we get exactly the same correlation as we got for the 20 features. So if you put a weight of 1 on these and a weight of 0 on these, we actually get the same correlation that we get with all 20 features. If we use these over here, we get much lower correlation. So this gives us a hint of what should be the critical features that are important for identification. And if we found those critical features, which are hair, eyebrow thickness, eye shape, eye color, and lip thickness, we should actually be able to now take a face, change it, and make it a new face. Okay, so this guy is a guy in which we change the hair color, the eyebrow thickness, the mouth, the lip thickness, and this is a guy in which we change 6 other features that are not critical, which would be the eye distance, would be the head proportion, it would be the mouth size, and what you see is that by changing this, we actually generated a new person here, and by changing those, we actually seem to get exactly the same person, or a very similar person. It's just another example. We change critical feature, we get a different person. We change non-critical features, we get a face that is more similar to the original one. So despite the fact that when we measure the face-space distance between these two pairs, we actually did not change them by much. So at the end, I think what we actually were able to do is that by describing a face as a feature vector and providing with the values that each of those features are describing it for a specific face, we were able to answer a very fundamental question about how face recognition is done by the brain. So how we can decide whether someone has a specific identity and what happens when we are deciding that it's actually a different person or a same person. Okay? So that's the first part in which I try to show you how we can use the same terminology and the same approach between the two disciplines in order to answer questions within the other discipline. The other question I want to talk about is the type of input that we want to give we want to provide the system in order to be able to get a good face recognition ability. So what I mentioned earlier is that in machine vision, we basically have the training set. We decide what is the training set. We give those images to the algorithm, and the algorithm is actually going to learn how to recognize faces based on this training set. In humans, we don't know what is a training set, but we know that the training set is actually important. Why we don't know? Because we don't know, we cannot follow people throughout their life and see which faces they were exposed to throughout their life. And when they come to the lab, we know that what they've seen before is actually influenced their performance in the lab. How do we know that? We know that based on those different phenomena that are very well known in cognitive psychology. This is called the other race effect, the fact that when you are coming to a different country with faces from other races, you find it much more difficult to recognize faces from other races than faces from your own race, and this is typically explained based on the experience that you had, because Asian faces, when they come over to Caucasian countries or to African countries, that would have the same difficulty in recognizing faces. So this by itself showed that the input that we give to the system early on would influence the way they would recognize faces later on. So this is one extreme in which we have very low experience with faces that then influences our ability to recognize the faces later. On the other hand, we have the familiar faces. Familiar faces, the faces that we've seen many different times. We've seen them in many different ways and lighting and poses and expression. And because we have very rich experience with the familiar faces, we are actually very good in recognizing familiar faces. So these are faces of familiar people, and even when the visual quality of the images is very low, you can easily tell that this guy is Woody Allen, and this one Bill Clinton, and this is Saddam Hussein. So although the quality of the image is very low, we've seen those faces so many times before, we have such rich perceptual experience with these faces, so even if I show you the image in very poor quality, you can still recognize it. So basically, we can think about it as something as a continuum. On one hand, we have the other race faces, in which we have little input, and this is where our system is not doing the job so well. On the other hand, we have the familiar faces. It could be famous faces, could be personal familiar faces. We've seen so many examples of them, so we're doing very well. But the question is whether this is the only factor that influences our ability to recognize faces. Another factor that seems to be important is the fact that whenever we see a familiar faces, we also provide it with a label. So whenever we see an image of Jennifer Aniston, you see the image and you immediately provide the image a label. And whenever you see a person you're familiar with on campus, you see the face and you immediately provide the face with a label. And this label may be important too. However, how we can dissociate between this perceptual experience and labeling, because usually when you have large perceptual experience, we also give this person a label. So we had to find a case where we have one but not the other. And this we found in this specific case, newborn faces. Newborn faces are also very hard to discriminate, like Asian faces. They all look alike. Why they all look alike? Maybe because we don't have much perceptual experience with newborn faces. We hardly ever need to discriminate between newborn faces and interact with them, okay? However, there's a specific population of people that have very rich perceptual interaction with newborn faces, and these are neonatology nurses. Now, they come to work every day, they see many many newborn faces, okay? Many. Every day they get a new batch, okay? So they get very, very rich perceptual experience with, over many years, with newborn faces, but what they don't have, they don't give them labels, because they don't need to give them labels. They come on one day, then they leave, they come in a new batch, they don't need to give them labels. So now we have an example of a case where we have very rich perceptual experience with no labels, and we can see whether rich perceptual experience by itself is the important thing. So we design a task in which we presented with subjects with other adult faces or newborn faces. They have to recognize them. We give the task to the librarian here on campus. They are our control group with the same age and gender matched to the neonatology nurses. We see that they recognize better adult faces than newborn faces. Okay, this is because they are not exposed to newborn faces but are exposed to adult faces. What will be with the neonatology nurses? Neonatology nurses are doing exactly the same. They've been exposed to a massive number of newborn faces, but this didn't improve their recognition ability, suggesting that at least in this case, we see that the massive perceptual experience that they have with the faces did not contribute to face recognition. We can learn something about the type of input that we need to give them. So what we did next, we got subjects to the lab. We showed them the newborn faces, but now we gave them name tags, okay? So they had to learn the name tag of each of those different faces, and we trained them on those faces. By the end of the training, they could tell that this is Ken, this is Tom, and this is John. At the beginning of the training, we see they do better on the adult faces than the newborn faces. At the end of the training, they are very good with the newborn faces. They can tell which is Tom and which is John. And interestingly, when we run them on a new batch of newborn faces they have not seen before, they are doing better than what they have done before the training, okay? Suggesting that minimal exposure to faces that provide you with some label about the face is important, okay? We recently ran a study in the lab which has tried to compare these two ideas directly. Illinois Schwartz in my lab is running this experiment. There is a poster tomorrow that you can go and see the additional information, but basically here we show the same thing. You expose subject to many different images of a person, and you see that this doesn't contribute much to the face recognition ability. You expose subject to only one view of a face, but you provide the face a label, and that increased face recognition ability significantly. What you'll see in the poster tomorrow, by the way, is that the human brain is very picky about the label. So in the algorithms, you can give any label, it doesn't care, but the brain does care about the label also, so that's for the poster tomorrow. Okay, so this is how the brain is doing it. The brain needs some perceptual experience, but it also needs some labeling. What about the algorithms? Today, when people develop algorithms to recognize faces, one of the benchmarks that they use to know whether the algorithms can recognize faces or not is the label face in the wild database. It's actually pretty complicated task for the algorithm. You present the algorithm with this kind of images. They are very complex images. These all belong to the same person, then the algorithm should be able to tell that all these images belong to the same person despite the very different views and expressions. And this database has 13,000 images, so the algorithm has to be very good in order to do that. And there's a recent review actually that tried to summarize all the different protocols that use this specific database and how well they were able to do this recognition on the label face in the wild. These different algorithms basically differ on pretty much the two dimensions that I just mentioned to you. How much data you provide to the algorithm and whether the data you provide is labeled or not. So what I did here is I tried to summarize the performance of the different algorithms. Okay, so this is how they are listed in the paper. These are the different algorithms, and they have different performance level. And this is the standard error. This is the difference in the performance level of the different algorithms. And these are just different protocols. So the difference between this protocol is pretty much the amount of data that the algorithm was presented with. So if you present the algorithm with more information, with more images, then it's going to do better. And this increase here is the effect of labeling. So these were actually provided more labeling to the images. They didn't only provide a large number of images, they also provide some labeling to the images. And that, you see, increased the performance of the algorithm as well. I just want to mention one specific algorithm that was developed here by Yovel from Tel Aviv University and the Facebook AI group. And these algorithms actually belong to this group. They both provided a large number of faces, 4 million faces, but the faces were also labeled, okay? So they had like 4,000 identities, 1,000 faces for each identity, all were labeled, okay? These are faces uploaded to Facebook. So Facebook had this very huge databases, and by combining both labeling and large exposure, you can see that the algorithm is doing well. So how this is related to the computational problem I mentioned to you earlier? I mentioned that we both need to do discrimination and generalization. Perceptual experience seems to be important for the generalization. We need to get many examples of the same person in order to be able to recognize the person on a new image we haven't seen before. But this is not enough. We also need to provide labeling, and this labeling is going to help us with the problem of discrimination. And this is how the brain and probably also the algorithms are able to solve this complicated problem that seems to ask the system to do two contradictory tasks. Okay, so I hope I was able to convince you today that despite the fact that those two different approaches are using a different type of information, they have different goals, they're still complementary, and I think they deal with the same problem, and at the end I think better communication between the computer scientists and the cognitive psychologists would benefit the field of face recognition specifically, but of actually studying the mind in general. I think the main problem we have today is that most computer scientists are not experts in cognitive psychology. Most cognitive psychologists are not experts in computer science. And this is why we opened last year, or this year actually, a new program in the Segal School of Neuroscience. The student just started, and they are going to do a double major in psychology and computer science. They're going to be experts in both disciplines and also get education in neuroscience, neurobiology of the brain. And we hope that this is the generation that is going to help us to solve the big question of how does the mind work. Thank you so much.